Hello students, in this lecture we are going to start chapter number 3, that is steady magnetic fields. In electrostatics we have seen all the things related to the charge. The charge was measured in coulombs and it is a steady charge placed at rest, and the quantities related with charge we have discussed in electrostatics. So the charge will generate an electric field, but in this chapter we are going to deal with current. So when charges are in motion, they will constitute a current, and magnetic field is developed because of the charges in motion, or when current flows, magnetic field is developed according to the Faraday's law that we know. In general, there are some basic properties of the magnetic field. First, we'll consider those properties, and then we'll find the relationship of currents with other quantities of magnetic field. So similar to electrostatics, there are many quantities related with current in magnetic fields, like magnetic field intensity, magnetic field density, etc. So let us first consider some basic properties of magnet and its field. We already know in physics that a magnet has two poles, a north pole and a south pole. The region around the magnet where its influence is felt is called as magnetic field. So whenever a magnet is there, the region around the magnet is called as a magnetic field. Any metallic part will experience a force if it is bring near about this magnet. These circular lines will indicate the magnetic field lines, and they are crowded at the poles and they move away from one pole and go towards the another pole. We cannot see the magnetic field, but it can be represented by a set of curves around the magnet, and these set of curves are called as field lines or magnetic lines of force. We have seen this in our childhood. This experiment we have also performed in physics. So these field lines indicate the existence of magnetic field around a magnet. The lines will start at north pole and end at south pole of a magnet. They are crowded at poles where the magnetic field is strongest. The lines do not intersect with each other. Each line is continuous closed curve passing through the magnet. Now, in electrostatic also we have seen this kind of field generated by a dipole and its movement, dipole movement. So, similar to magnetic field, there is a field in electrostatic also, but it is generated only when there is a dipole present or plus q and minus q charge is present. We have seen it. So, both fields are similar. So, we can say that there is a resemblance or the similarity between some magnetic field and electric field. So, with this basic property, let us start with the first concept of the magnetic field. As we have seen in the electrostatic that whenever two charges are present close to each other in space, then one charge will exert a force on other because it has generated its own field, or another force may exert a force on first charge, like that. But here there are no charges. Here there are charges in motion that we call as current, and because of those current carrying conductor, there may be some forces existing in the magnetic field. So forces between current carrying wires present. Familiar examples that we use to determine this magnetic force field will look like in the following diagram. So here in the first diagram, you can see there are two forces I1, there are two currents I1 and I2. Both the currents are flowing in the same direction. So there is a force of attraction. In electrostatic, when two charges are similar, there is a force of repulsion, and when the charges are different, plus and minus, then there is a force of attraction. But here in this case, there are no charges, there are currents. So I1 or I2, if they are flowing in same direction, upward or either downward or along any particular axis, then there is a force of attraction. or it is called as attractive force. If one current is flowing in one direction and another current is flowing in exactly opposite direction 180 degree, then the force between the two currents is repulsive force, and this is the force due to magnetic field, because this current causes a field around it, this current causes a field around it, so there is a force between these two fields, repulsive force between these two fields. And third diagram, one current is shown like this, going maybe upward, and another current is perpendicular to the direction of this current. I2 is shown as perpendicular to the direction of I1. So it is shown as a dot sign. This is a convention to show the current, or the method which is which will indicate that either the current is going into the paper or it is coming out of the paper. Now in this case, suppose that I2 is going inside the paper and I1 is in the upward direction. So this means they are perpendicular, mutually perpendicular to each other, and in this case the force will cancel. One force is positive, another force is negative, but they are exactly opposite, so equal, and so they will cancel. So in this case the total force is 0. So this is the basic considerations regarding the forces in magnetic field. There is no derivation required here, and we are going to directly discuss the next point of the magnetic field, and that point is Weyer's law. But before that, let us see one more few concepts. So similar to the electrostatics, uh, in electrostatic we have seen there is a electric field intensity, and that is denoted by E bar. In this case, we are going to denote magnetic field intensity by H bar. Magnetic field intensity by H bar. What is that intensity? So whenever a current flows through a coil or through a wire, then there is a field developed across around that wire, and that field is indicated, its intensity is indicated by H. We are going to see the derivation for this H, and its direction is determined by right hand rule. Its direction is determined by right hand rule. So if see again the same diagram is there, two currents are there, both are flowing in the same direction, but the intensity generated by I1 is in circular direction, anti-clockwise direction, and there is no intensity at on wire 2, at the location of wire 2, because this path enclosed has enclosed only wire 1. This path has not enclosed wire 2, so there is no intensity at this point, though there is a force of attraction, because both the currents are flowing in the same direction, attractive force in the direction given by, so the force is given by the direction I2 cross H. There is a cross multiplication, or cross product between I2 and H. In the second diagram, see here, I1 and I2 are in opposite direction, though they are in the same direction or the opposite direction. The condition is that the path of H, which is circulating the I1, should be such that the another conductor must be inside that path. But in this case, I2 conductor is not in the path, inside this circular path, so there is no field generated at this point. Okay, because of I1 only H is generated, and because of I2 no field is generated. So these two fields are opposite to each other. There is a force of repulsion. So H from wire 1 at location of wire 2, they have shown by a cross sign. So repulsive force is in the direction of I2 cross H. So whatever the forces are there, repulsive or attractive, they are given by the current multiplied by second current multiplied by field due to the previous current, like this. Okay, so what is the definition of H and how it is derived, that we are going to see using Biot-Savart law. So H is again called as magnetic field intensity, and it is related to the quantity B, that is magnetic field density, and B bar is equal to mu naught H bar. Magnetic field density is equal to mu naught into H. That one more relationship we are going to derive later on. So these two are the main two things, H and B. Let us first see the first law of magnetostatics, that is Biot-Savart law. This law gives the relationship between H and I, or it indicates the how magnetic field intensity is described, or how it is given by equation. So Biot-Savart law is used to determine the magnetic field intensity H near the current carrying conductor, or we can say it gives the relationship between magnetic field intensity generated by its source current element. Now in all magnetic fields henceforth we are going to see the current element I multiplied by a small length dl. There are no charges, no point charges, no surface charges. There are currents placed on a line, placed on a surface, or placed on a volume. The currents are placed, not the charges are placed. So IDL is a small current element, or the current part, current carrying part. DL is a small length. So it is IDL means current carrying small element. If such kind of element is there, or such current carrying conductor is there, then what is the intensity at point P? That this intensity is given by Biot-Savart law. The Biot-Savart law states that the magnetic field intensity at point P due to current I flowing through a small element dl is directly proportional to the current, that is I, in amperes. It is also directly proportional to the length of the element, that is dl. It is directly proportional to the sine of angle theta between the direction of the current and the line joining point P with dl. So this theta is the angle between them, and it is inversely proportional to the square of the distance r or x of the point P from element dl. So dh is given by some constant k, proportionality constant k, into I into dl into sine of theta divided by r square, capital R square or small r square. So this is the confirm equation. The length dl bar and ar cap are to be taken in the cross product, because we have written in the previous equation dl sine theta. So I can write this dl sine theta as dl sine theta into 1, where dl is magnitude of dl bar, 1 is magnitude of ar cap, where ar cap is unit vector along this r direction towards point P, and sine theta means angle between these two lengths, dl and r. So we can write this dl sine theta into 1 as dl bar cross ar cap. Okay, so dh bar becomes idl cross ar cap divided by 4 pi r square, where 4 pi is constant, proportionality constant. The intensity is measured in ampere per meter. This is the unit of intensity. So, and this dl bar and ar cap is nothing but the cross product of this length and this length, where ar cap is a length or the unit vector indicating the direction of joining of point P with dl bar. So magnetic field intensity is a vector quantity, and it is the direction of this h bar is given by right hand rule. What is that rule? So if we consider this figure, a right hand rule, thumb rule, is used to indicate the direction of h bar or b bar. So see in this figure here, the thumb is indicating the direction of the current flowing through the conductor, and if you hold the state conductor in the right hand such that the fingers are curled around the conductor and the thumb is straight indicating the direction of the current, then this curl finger indicate the direction of magnetic field or lines of field or b bar. So these lines are, now in this figure, these lines are in anti-clockwise direction and the current is going in upward direction. So if you indicate the direction of current in the downward direction, then this uh, lines of field will be reverse of this whatever we are seeing right now. by convention there is a meaning of how to represent the current is going, whether it is inside the paper or outside the paper. So for that convention, this figure is considered. See here, a dot sign is indicated, and it indicates that the field is in anti-clockwise direction, and the current is coming out of the plane. The circle with dot sign indicates that the current is coming out of the plane. So current direction is perpendicular to this plane. Current is coming out of the plane, and in this direction there is cross shown, and cross means the current is going inside the plane of the paper, and the field is in clockwise direction like this. Okay, so these two conventions are considered for calculating the direction of the magnetic field and calculating the direction of the current. In general, we have a relationship between the intensity and the flux density. So B bar is equal to mu into H bar. So flux density will have same direction as that of a H bar. Now in general, what is the equation? Final equation is dH, that is differential field intensity, is equal to IDL cross AR cap divided by 4 pi r square. And this intensity can be considered because of full loop, complete loop, current carrying loop placed in the magnetic field. So this IDL is a smaller element, so we have considered this IDL, and we have find out DH at point P. If I want H because of complete wire, closed wire, then it should be a closed integration of IDL cross AR cap upon 4 pi r square. So this is the total H in ampere per meter arising due to closed circuit path. Arising due to closed circuit path. Similar to ideal, there are various elements, current elements. In case of ideal, the current is present on a small length. The current may be present on a surface area like this. It is distributed on the surface area. So this kind of current is called as a surface current. If I multiply this K, it is measured in ampere per meter or ampere per meter square, and if I multiply it by the length B, then I will get the total current in this area. Okay, that is called as I. So like this we can represent different current elements. So if the current is distributed on entire surface with width B and length L like that, square surface, then it is known as K bar ds. So instead of IDL, we can use K bar ds if the surface current is given in ampere per meter square. So in equation of H, IDL we replace it by KDS. Similarly, the current may be present inside this complete volume. If you consider this sheet as a volume, then the current present inside this volume with breadth, height and length, it will become a volume. So that current is known as volume current density. And instead of IDL, we can use JdV, where J is called as a volume current density. J is called as volume current density and dV is small volume. So instead of IDL in the equation, we can use JdV, and we can write the volume integration of JdV into AR cap divided by 4 pi r square. This is surface integration and this is volume integration. So the current can be of any type, just like that of charge. Charge was present at point, charge was present on surface, charge was present on line. Similar to this, that the current is also present on the length, it may present on a surface or it may be present in a volume. So for these three types of distributions, we can find out H for each case. Now we are going to derive an equation for finding H, that is magnetic field intensity, if an infinite current carrying conductor is placed along z axis. And because of this current, what is the field surrounding that conductor, what is the equation of that field, we are going to derive this. So first let us place that current wire along the z axis. Let capital I be the current flowing through the that wire. Consider small element dl at point z dash on z axis, and let we want to find out the intensity on in xy plane, either exactly on y plane or in xy plane somewhere here. And so this idl will be the current element. Now we have to what to do, we have to join this idl to point p. Suppose we want intensity at this point, so I will join this point and this point, and this is our vector r bar, right? Then what to do first, ideal we can draw a perpendicular from this point p, for example, onto the z axis. So this is our perpendicular distance, minimum distance between this current element and this point p, right? So ideal is equal to, we can write ideal, instead of that we can write an in equation form. If we consider the Cartesian cylindrical coordinate system, then ideal, what is dl bar in cylindrical system? It is dz az cap, because the direction is along z axis. So ideal we can write simply as I into dz az cap. Then we are going to use the Biot-Savart law to solve the to find out the final formula for intensity due to infinite current carrying filament. So let us move. Now what is the formula state? It requires an ideal element. We know already this one, we can place it here. What is AR cap? That we have to find out, and what is R square? That we have to find out. And this integration should be from minus infinity to plus infinity. So what is R bar? R bar is the distance between this point where dl is present, current element present, and where you want to find out the intensity. Now this point has a coordinate, idl has a coordinate, it is placed exactly on z axis. So let us, r is equal to 0, phi will kept as phi, and z is z dash, because this is the z distance of the point. And for this point r is rho, because we have indicated this as a rho, you can use r sign also. So rho comma phi comma 0. Why 0? Because it is exactly in xy plane where z is 0. Now after joining these two, let us find out the vector r bar. So r bar is what? Rho minus 0 ar cap, or rho minus 0 a rho cap, minus phi a phi cap, plus 0 minus z dash a z cap. 0 minus z dash a z cap. So it will become rho ar a rho a cap minus z dash a z cap, and the magnitude of this r is equal to r square plus z dash square, right? So what is ar cap? This is ar cap minus z a z cap divided by, I will call it as r square plus z dash square, right? So we'll put, what is dh now? Dh is equal to idl as it is, ar cap is what? This complete equation, and divided by 4 pi r square. Again r square is what? The square of this square root r square plus z square. So that total will become r square plus z square raised to 3 by 2, if we put all the values in this equation. Now we have to integrate this equation from minus infinity to plus infinity. Okay, so the equation has been simplified somewhere here. Now see here, here az cap is there, and there is a cross sign between ar cap and az cap again in this bracket and here. So there is a cross sign. So we have to take the cross multiplication considered. Here we have to consider the cross product, not the dot product. So what is az cross ar? What is az cross ar? That we have to see. So the next equation will be changes to somewhat simplified version. For h is equal to minus infinity to plus infinity I dz, instead of dl, I think instead of dl we have put dz az cap, right? And this equation has been formed. So 4 pi and I are constant, that is taken outside. Now this az cross ar we have to find out. So az cross ar is what? We know these identities, az cross ar, the third one, is equal to a phi cap. So we'll put az cross ar is equal to a phi cap. Okay, and if I multiply this Az to the second bracket, Az in cross minus Z dash into Az. So Az cross Az is 0. So this term will be 0, second term. Multiplication of this with second term will be 0. So it automatically cancels. So what we left with? I upon 4 pi integration minus infinity to plus infinity. R was there, that we call as rho. Dz was there and a phi cap is there, divided by r square plus z square raised to 3 by 2. Now to solve this integration, we have to use limits. We have to put some identities. So let us put z is equal to rho tan theta or r tan theta. So dz is equal to rho sec square theta d theta. As z tends to infinity, theta tends to pi by 2, and if z tends to minus infinity, theta tends to minus pi by 2. So after putting this in equation, the equation will become I into rho, then this dz we have to replace it by, or dz dash we have to replace it by r sec square theta d theta. So r sec square theta d theta is there, a phi cap is there, divided by 4 pi divided by r square plus z dash square will become 1 plus tan square, uh, 1 plus tan square theta, r square tan square theta, r square will be taken common. So now raised to 3 by 2 is there. So again 1 plus tan square theta is equal to sec square theta raised to 3 by 2. So it will become sec cube theta. So after solving this all the things and putting the limits from minus pi by 2 to plus pi by 2, will get d theta into a theta cap divided by r into sec theta or rho into sec theta. So we will take this rho outside again, and 1 upon sec theta is equal to cos theta. Integration of cos theta is sin theta, from minus pi by 2 to plus pi by 2. A phi cap is as it is. So after putting the limits, sin pi by 2 minus of minus sin pi by 2, that is equal to 2, and 2 and this 4 will cancel. So it is I upon 2 pi r into a phi cap, and this is called as equation for magnetic field intensity H bar due to a current, infinite current carrying filament placed on z axis, and a phi cap will indicate the direction of the H. So what is a phi cap? How a phi cap is measured? How a phi cap is measured? How it is shown? So if this is your this is your filament, then phi direction is like this, na? It is in 360-degree, right? So this is your phi angle. We measure it from in clockwise direction in xy plane. So this a phi cap indicate the direction of h bar if I is flowing in along z axis. In this way h bar is indicated, and b bar and h bar, that b bar means magnetic field density, are related by a letter or permeability, that is mu naught. So b bar is equal to mu naught into h. So that equation will become mu naught 1 of I upon 2 pi r into a phi cap. Now to where a phi cap is what? It is the direction of h bar, and it is obtained by taking cross multiplication of al length vector and the line joining the conductor and the point P, AR cap, that we have already considered. Now consider this example. Using Wyatt-Short law, find H in Cartesian components at point P 2, 3, 4 if there is a current filament placed on z-axis carrying 5 milliampere of current from minus infinity to plus infinity. So this is the example to find H bar due to infinite current carrying filament. So what is the procedure? Let us check. Also, there is second option, that find H at the same point if the filament is placed at x equal to minus 1 and y equal to 2. Now, to solve this example, we have this equation H bar is equal to I upon 2 pi r into a phi cap, where Fi cap is Al cap cross Ar cap, remember. And what is Al cap? Al cap is the direction length of the filament. So in our case, the filament is placed in on z axis. So Al cap is equal to Az cap. And Ar cap we are going to find out by finding R bar, vector R bar. Okay, so how to solve this? Let us check. So first let us draw the Cartesian system, x comma y comma z, and then let us place that filament. Suppose the filament is placed on z axis like this, and we have to find out the intensity 2 comma 3 comma 4, right? So 2, 3 and 4. So somewhere here the point P is situated, 2 comma 3 comma 4. Now first thing in this solving example is to draw a perpendicular point from point P onto the filament. So filament is z axis, so we'll draw a perpendicular on z axis. Find the foot of the perpendicular. Z axis means z value, no x value, no y value. So it is 0, 0, 4. We are going towards point P. So this is our R bar, right? So what is R bar in this case? R bar is equal to, the filament is carrying 5 milliampere of current in, let us consider this direction, upward direction I. So R bar is what? 2 minus 0 Ax cap plus 3 minus 0 Ay cap plus 4 minus 4 Az cap in simple Cartesian coordinate system. So R bar is what? 2Ax plus 3Ay plus 0. So magnitude of R is equal to square root of 2 square plus 3 square. So that is equal to 4 plus 9, that is equal to square root of 13. This is the magnitude of R. Now we want unit vector AR cap. AR cap is equal to vector divided by its magnitude, that is square root of 13. Now what is equation? H is equal to I upon 2 pi into R, or let us call it as capital R, AR, A phi cap, right? A phi cap it is. And what is A phi cap? It is AL cap cross AR cap. Remember, this is very important thing. Now AL cap is what? What is AL cap? AL is where the filament has been placed. It is placed along z axis. So the AL cap is AZ cap. We'll consider it as plus because our current is going in upward direction. We have considered that. Okay. And what is AR cap? AR cap we have already calculated as 2AX plus 3AY divided by square root of 13. Now we have to take the cross product of AL and AR. So A phi cap is equal to AL म्हणजे AZ cross in bracket, here we have to place a cross, and here 2AX plus 3AY divided by square root of 13, that we have to take cross product. Now what is the cross product of this? Let us rub this. So A phi cap will become, now take AZ cross AX. What is AZ cross AX? Z to X, that gives us Y, right? So it is clockwise and anti-clockwise. So it is x comma y comma z, x to y clockwise, y to z clockwise, z to x clockwise. So it will give us plus ay cap. So it is az cross ax is equal to 2 times plus ay cap plus. Now next is az cross ay. Az cross ay. So az cross ay. So here we have to go in the reverse direction. So that will come as minus of ax cap. minus of ax, but there is a coefficient of 3, so it is minus 3ax cap divided by square root of 13. I keep it as it is. So this is our final ay cap, sorry, a phi cap, because we have to take the cross product of al and ar. Correct? What was our ar? 2ax and 3ay was our ar. Now it has changed to this value. A phi is now this one. 2ay cap minus 3ax cap square root of 13. So 2ay cap minus 3ax cap square root of 13 as it is. That is our a phi cap. Now let us find the final thing, h bar. What is I given? 5 milliampere. So 5 into 10 raised to minus 3 divided by 2 pi r. So it is 2 into pi into r is square root of 13 into 2ay cap minus 3ax cap divided by square root of 13. So after solving this, whatever you will get, square root of 13, square root of 13, 5 divided by 2 into pi into 13 into 10 raised to minus 3, 2ay cap minus 3ax cap. So after solving this, whatever you will get, let us find out the solution of this example. So it is 5 divided by 2 divided by 3.145 is equal to divided by 13. So it is 0.061 into 10 raised to minus 3 in bracket 2ay minus 3ax. Okay, or we can write it as 61 into 10 raised to minus 6 into 2ay minus 3ax, or we can take this multiply this 2 6 12 ay cap minus 3 183 ax cap whole into 10 raised to minus 6 ampere per meter. This is the unit of h bar. So in this way we have to solve the example based on h bar. This is one part of that example. What is the second part? Second option is they have given that the filament is placed on at some another point. It is not on z axis. So where it is placed? It is placed at x equal to minus 1, and what is given? X equal to minus 1 and mm, x equal to minus 1 and y equal to 2. So x equal to minus 1 means somewhere here, here, and y equal to 2 means this point. Okay, so from this point the filament is going. So it is going parallel to z axis. So our filament is going, in this case it is parallel to z axis, going from this point where x is equal to minus 1 and y is equal to 2. See now, where our point is 2 3 4. So point is here, so point is somewhere here. So 2 comma 3 comma 4, and again the same thing. Now instead of z axis the filament is placed somewhere else. Now again the same thing, we will draw a perpendicular from this point onto the filament, and this is our r bar in this case. So r bar will change. Only thing is the r bar will change. So what is r bar? What is the foot of the perpendicular? It is y equal to 2, x equal to minus 1, And what is Z? Z is taken from this point. So Z is 4. What is R bar? 2 comma minus of minus 1. 2 minus 1 into AX cap plus 3 minus 2 into AY cap plus 4 minus 4 into AZ cap. So R bar is equal to 3 AX cap, minus minus will become plus here, plus 3 minus 2 1 AY plus 0 AZ. So R bar in this case is equal to square root of 3 square plus 1 square, that is equal to 4 plus 1, that is 5, square root of 5. So mod of R bar is square root of 5. Then the main thing is finding A phi cap, because what is H? H bar is equal to I upon 2 pi R into I upon 2 pi R into A phi cap. That is the equation. So what is A phi cap? AL cross AR, right? So AL cap in this case, the length is, it is again parallel to Z axis. So we'll take this as AZ again, AZ cap again, because it is parallel to Z axis. So the length is AZ cap, and cross will take the AR cap. So what is AR cap? AR cap is our equal to 3x plus 1 AY divided by square root of 5, that is our AR cap, by this and this formula, right? So we'll take the cross product now. What is cross product now? A phi cap, we'll write it again, AZ cap cross in bracket 3, what is the equation? 3AX plus 1 AY divided by square root of 5. We'll take the cross product of AZ cross AX, that is AY plus AY, and 3 is already there, so 3AY plus AZ cross AY, so XYZ, AZ cross AY, we are going to reverse, so it is minus of AX, and there is 1, so it is 1 divided by square root of 5, that is equal to 3AY cap minus AX cap divided by square root of 5, that is my A phi, right? And then we'll find H bar now. H bar is equal to I, that is 5 milliampere, sorry, 5 milliampere divided by 2 pi R, R is square root of 5, into our A phi cap has become, 3 AY minus AX upon square root of 5, correct? Yes. Then solve this. So it is 5 divided by 2 pi into 5 into square root of 3AY minus AX, that is equal to 1 upon 2 pi into 10 raised to minus 3 AY cap minus AX cap, whatever it is. So you can multiply by this quantity to the bracket and then solve it again one more times. So 3 divided by 2 pi AY cap, I will write like this, AX cap into whole into 10 raised to minus 3 ampere per meter. So this intensity is again in ampere per meter, right? So this is the value of the intensity.